Okay, so now let us begin this one. So in the introduction on AI and ML, let us quickly see about what is ML basically. This is the institute, and see, in the evolution of the human civilization, there are so many inventions that happened. The wheel was invented, compass was invented, so many things were invented. And when it comes to the recent times, the electricity invention is one of the biggest things. Before that, steam engine was invented. Okay, now computer invented in 1822, basically. The mechanical computer by Babbage was invented in 1822. It was a big machine. Later on, a telegraph came into picture, telephone came into picture, automobiles, airplanes, and the electronic digital computer came into picture in 1945. Okay, so the transistors as revolutionized, and today we are having personal computers from 1970 onwards. Mobile phone came in 1973, internet came in 1983, smartphone came in 1992, so on. The era of artificial intelligence started in 1955 onwards. It was started in 1955 itself. So one can see that the evolution is going on like this. Maybe the next, we're going to see robots or something like that. We're going to see already automation is taking place. Okay, and we know that nowadays even children are playing with electronic devices. So when it comes to artificial intelligence, from 1950 to 1990, it was basically rule based. That is, this is also called as deductive learning. Deductive, we'll see, maybe briefly we can see what is this one. Uh, for example, like playing chess, something like that. But from 1990 onwards, it went on to inductive learning. Inductive learning means learning from the data directly. So that's what we are calling as machine learning. And in this machine learning, nowadays, we are in the era called deep learning. Okay, so the artificial intelligence name was first coined in 1956 at a conference. So AI means this is like the machine should be able to do as humans are doing. This is one of the definitions. This is what it is saying. And AI as such is an interdisciplinary field across many domains. Okay, so nowadays we have achieved these things more or less we achieved. For example, board games, we are able to do this one. Solving puzzles, we are able to do. A Google map is there, which can show us the map. And image and speech recognition enhancement, all these things we have achieved sufficiently. And these things, most of you might be knowing these things. We are able to recognize the handwritten characters or something like that. We are able to understand speech. We are able to use AI in the medical diagnosis and in some other computational chemistry and so on. And in future, so this may be interesting, in coming years, what is that we are expecting to see? See, the translating languages is already taking place, but it will come into full force. You can talk to some other person in some other country where the language translation is going to happen seamlessly. Seamlessly means without your knowledge, maybe in between it might be happening online. And then writing high school essays, still this is an art for us. We don't know how to write an essay, or still driving a truck is a problematic one. Auto driving a car, automatic car driving is nowadays available, but still driving a truck automatically is still not there. And if you see this one, the machine is going to do the work of a surgeon as a doctor by 2053. And uh, in coming 100 years, the machines are going to outperform humans in almost all activities. This is a fact. If we may not be able to live up to this 120 years, but if nothing is going to happen, civilization is going to progress like this. After 100 years, maybe almost everything will be automated. There will be intelligence in almost in every application. Okay, so this one was obtained at a conference. When it comes to the techniques, machine learning techniques, we are having, as I said, deductive learning is there, inductive learning is there. Deductive means the rules are given ahead. For example, how to play the game, what are all the legal moves, all these things are hard coded into. That means we are going to write the program and the machine is going to play. For example, if you take two numbers and if you give the algorithm to multiply the two numbers, the program is going to multiply the two numbers, right? So this is also a kind of learning, right? Now the machine is able to multiply the numbers, isn't it? But we told the machine how to multiply the numbers. Step-by-step process is given by us. So here in the deductive process, the machine will not go wrong because we are giving the rules of the game. We are giving, so the machine will not go wrong actually, right? Multiplying two numbers, the machine will never go wrong except in some extreme cases when we are having two big numbers or two small numbers, the machine will not go wrong. Okay. Whereas the other kind of learning, which is more interesting, is called as inductive learning. Inductive learning means here we are going to give the examples saying that, for example, I will give one example saying that this 2 and 3, if I give, the output has to be 6. If I give 10 and 20, the output has to be 200. So like this, I am going to give some more examples, but I will not tell that this is multiplication and there is a technique for doing the multiplication. What I am going to do is that I am going to give the input and output. Several examples I am going to give. For these inputs, these are the outputs. That's all. I will not give any other thing. Now the machine has to point out how the input is mapped to the output. Okay. So this is learning from the examples or learning from the data. So it's called as inductive learning. So this is something like reverse engineering or something like that. Okay. So machine learning mostly comes into this one, where we give the examples, we ask the machine to learn from the examples. Okay. So now the board games, these are in AI, we know that how to solve these things, the rule-based things, the checkers or chess and all these things. For example, for tic-tac-toe, the tree kind of thing is explored. You might be knowing that DFS, BFS, and A-star algorithm. All these things are there, which are going to explore this one. The game trees are available, which are going to do the okay. So see, the deductive method has failed actually. This is not sufficient for us. Why? Because we ourselves don't know how we are solving the problems. See, giving rules can work for playing games kind of problems where we know, but you cannot give rules for a self-driving car. This attempt is going to fail. How many rules we are going to give for self-driving car? Similarly, for face recognition or for speech recognition, we can't give the rules saying that if these are the features, this is the style of speaking, something like that. If this is true, that is false, then he is the person. This kind of encoding our knowledge is not possible for certain tasks, especially for something like intelligent tasks like face recognition, speech recognition, something like that. It is not possible for us how to create a machine based on the deductive learning. So one has to go to the inductive learning. See, this is something which we must go into the inductive learning. So it means that we will not give explicit rules, but we are going to give examples, saying that this is good, this is bad, or something like that. We are going to say this example is a good example, or this is a cat picture, this is a dog picture, something like that, or this sound signal is saying this one, this is there in the sound signal. So these things we are going to give as examples, and then we will ask the machine to learn. Now, given a face, you have to say who is the person. So something like that. So this is called as inductive learning. So machine learning comes mostly into this one. And traditional AI goes into this one. Traditional AI goes into the board games and all these things where we know the rules. Will go into the first one. Machine learning will go into the second one. Okay. Now, machines can learn from the data actually. So examples means data. We are going to give the data. So we are going to give the data, we are going to give the algorithms. The learning is going to happen from the data. Okay, so this is what is called as machine learning. And we know that machine learning is a subfield of AI, and it is going to focus on mathematical or algorithmic aspects of learning, which can be programmed over a machine. There are various learning paradigms are there, and if you want to become an expert in the machine learning, then some prerequisites are there. If you have some proficiency in probability theory, linear algebra, calculus, something on algorithms, programming, if these things, some level of proficiency is there, then you can become an expert in ML by working for a few months, like 3 months or 6 months. You can become an expert in machine learning. I think some of you have turned on the mic or something like that. Huh? Jivita. If you are having any questions, you can ask me in between also. So quickly after this, we will go into the deep learning introduction by my colleague, Dr. Shivaram Dubey. But let me quickly complete this one so that, so the inductive learning, supervised learning is there, unsupervised learning is there. There are something called as reinforced learning is there. Okay, and these are the learning strategies which can be seen as from the examples how to build the system. But in order to build the system, some of the pre-processing steps can be done. One of the important pre-processing step is how to get the features. What are the important attributes to solve this problem? Okay, supervised learning means we are given the data with the labels. For example, we will give the dog pictures, we will give the cat pictures. For example, for a child, if we show these things, then we will ask the child to see these things, then we will give the child a new dog picture and then ask the child, what is this? The child is going to say it is dog. That means the child has learned to discriminate between these two classes. Okay. This picture is not available in the training set. See, the training set I gave is this one. These are the training examples. That which I gave to the child is not available in the training set. So then only I can say that the child has learned to discriminate between the dogs and cats. Okay. Now, the child has done something more than just remembering. Okay. So what we say is that child has learned the pattern, that is the regularity behind all dogs and the pattern behind all cats. Okay, so this is what the child has learned. There is some regularity behind all images of cat images and all images of dog images. That the child is able to learn. So now the important thing is that can a machine do this one? Can a machine find what is the regularity behind a class of examples? So that given a new example, it will say that it belongs to this class. Okay, so for this one, normally what we do is that if the cat picture is given, for example, if this is a cat picture, something like this, we extract features from this one, maybe by using various image filters or something like that. We are going to extract the features. These features typically will be numbers. So when you see these features, it is going to form a vector. It's a vector of numbers like this. Okay. We will call this one as, traditionally we will call this one as capital X, the vector of this one. So this is the actual object. For example, cat picture or whatever is that is this one. Okay. So the pre-processing is from the cat picture getting this picture vector. Picture vector means it's a vector of numbers which is going to represent the cat picture. We can work with this one. Okay. So now these feature vectors, we can, if you take all feature vectors, we can say that it is going to form a feature space. This feature space, we can call it as this symbol, cut X. And now there may be cat pictures or dog pictures. So there are labels for these objects. So some vectors label is cat, for some vectors label is dog. So there are labels for these things. So the labels may be coming from this set. So capital Y may be, now capital Y is, in our example, it is a dog, cat. Okay. For one example, the label, that is small y is dog. For the other example, maybe the small y is cat. So the label is coming from this set. Okay. So now our problem is, given this X, that is given the feature vector like this, one has to identify whether it is a dog or a cat. This is what is called as the machine learning classification problem. Okay. So what is that we are trying to do? In this feature space, if I give you any point in this feature space is X. X is going to have these attributes. Then one has to output the label. So one has to learn this function F, which is going to map the feature space to the class labels. Right. So learning this function F from the given examples, X, Y examples are given to us. Many XY examples are given to us. Some small y may be cat, some small y may be dog. Many examples are given. From that, one has to learn this one, so that if I give this X, it has to output me whether it is cat or dog. Okay. So this is what is called as machine learning problem. Okay. Now, this is one simple example. For example, the object is a person. A person may be represented with the height and weight. Now, the label may be overweight, normal. Now, the classification problem is, given a person's height and weight, you want to classify the person as overweight or normal person. That means you want to learn this function, which is going to map. Now, the feature space is having all points with the two coordinates, height and weight, two coordinates are there. Given this point having height number, weight number, it is going to give the label. The label is overweight or normal. Okay. So typical machine learning is going to have like this. If we are going to get from the sensor, the physical object is sensed, for example, image or speech or text or whatever is that is sensed. Then pre-processing, is going to extract the features, and these features we are going to use along with the labels, all these things. We are going to build a classifier. That means we are going to create a function F. So this function F is going to output the class. Okay. So once we are going to create function F means we are having a classifier. Then this classifier, which is function F, can be evaluated. What is the accuracy of this function F? All these things can be done. But basically, this is the steps in the traditional machine learning. Are you able to understand? I think most of you might have studied this one. Now the features, good features has to be like this. This is bad features. If it is going to be overlapping, features has to be like this. Okay. Now what happened is that traditionally it was like this. This is the traditional machine learning, right? We are going to extract the features, and then the machine learning algorithm is going to build the classifier. So this is going to create the classifier F. Okay, this is the traditional machine learning. But nowadays, this pre-processing step here, from the input extracting the features, this pre-processing step is also merged into the learning algorithm. That means now this pre-processing has become part of the learning itself. It has become here itself. So this whatever is there here has become part of the learning technique itself. The learning technique itself knows now what is the good feature extractor and what are the good features for the given problem. Okay, so this is what is called as deep learning, in the sense that the pre-processing is consumed as part of learning. So because there are various pre-processing strategies are there, which pre-processing strategies are good for this problem, only that problem can say that, right? So now, while addressing the problem, we learn what are the good pre-processing steps. Okay, that means while learning to classify an example, that is here, the example is the picture itself, the cat picture itself we are going to give. Now, how to extract features from this cat picture is also learned along with this function F. That means now this entire thing is called as function F. In this entire thing, the feature extractor is also learned. Okay. So this type of thing can work better with the signals like images, speech, sometimes even with the text. But there is a difference how it is going to work with the text when compared with other type of data like images or speech or video. So our FDP is this deep learning models for natural language processing. Okay. So here also we are not going to extract the features first, and then we are not going to create the classifier or something like that. But we are going to work with the raw data, that is the text, and we are going to learn maybe to classify the text as sports text or news text or whatever is that, or to understand what is there in the text, or to summarize the text, or to compare that two texts are saying the same thing, or given a text and a question, answering that question. So all these things can be covered in this machine learning processes. So we are going to cover natural language processing using deep learning. Earlier, some 10 to 15 years back, it was traditional. Even in text processing, it was like this only. But nowadays, in the text processing or in the natural language processing, it is like this. Okay, so there are other things are there. See, now sometimes just remembering, some people say that, why can't you simply remember, if you want to classify, simply remembering is called as rote learning. That's not a classifier. There are various classifiers are there. Artificial neural networks is one of the important class of classifiers. Within this one, deep learning is a specialization. Deep learning means there are many layers are there in the artificial neural network. There are other categories of classifiers are there, generative, discriminative classifiers. These things, maybe as we go ahead, we will learn about these things. One of the easy classifiers most of you might be knowing is k-nearest neighbor classifier. For a given example to be classified, for example, this one, we will find k neighbors of this one, and based on the majority vote, we will assign the label for the given test example to be classified. Here the red thing we want to classify. There are two classes. Blue class is there, white class is there. The red point we want to classify as blue or white. Okay, so we will take, for example, if k is equal to 1, we are going to assign that one to white class. If k is equal to 3, we are going to assign that one to the blue class. Right, so this is a classifier basically, simple classifier. Similarly, the linear classifier is there, which will say that which will try to find the hyperplane or a line on one side, one class, other side, other class. It can say like that. It's called as perceptron. Similar to this one, the next level to perceptron is called as support vector machines, which is also called as the best perceptron. We are going to find the best linear separating planes we are going to find. And then neural networks are very important for us. We believe that it is the inspiration for this one came from the biological neurons, that is from the brain. So there are some units called as neurons. So each unit is going to compute something and it is going to feed its output to the next neuron. So if the neurons are organized in the form of layers, we call this one as feed forward neural network. So this is the first layer where the input is fed into this one. This is the second layer, this is also called as the hidden, and this is the output layer, which is going to give the output. Okay, so this is layered architecture of the neural network. So that's why we call this one as feed forward neural network, because the information is going to go forward from the input layer to the hidden layer, to the hidden layer, to the output layer. And if you see one of the neurons, the input is going to come, for example, this neuron, if you are going to see, it may look like this. We will see this one in much more detail. There is going to be an activation function and all these things are there. Okay, so nowadays the deep learning means if this is the input layer, there may be many layers are there. Okay, many layers of hidden neuron layers are there. So in this case, there is first hidden layer is there, second hidden layer is there, third hidden layer is there, finally there is output is there. So directly the image, raw image is given here. We haven't done feature extraction. So nowadays what is happening is that this number of hidden layers can be something like 40, 50, 100, 200 like that. And it is able to solve many complicated problems. Okay, so there are other techniques are there, and we don't have any best classifier, and there is something called as generalization ability for a classifier, which is to avoid overfitting. Overfitting means learning unnecessary things has to be avoided. You should not learn unnecessary things, right? How to avoid learning unnecessary things, so that you are going to learn the essentials. You are not learning some random noise that is somehow came into the data. Okay, there are other ways in which one can diagnose the classification technique. There is the error can be diagnosed. See, if you want to diagnose how good is this function f, one can diagnose this function f. There are various things are there. Bias is there, variance is there for this one. So these things are going to tell us how good is your classifier, how good is your learning technique. Okay, so these things are somewhat advanced things. Overfitting, as I said, is a complex classifier. Then the next important thing is that in feature extraction, what happens is that what are the good features? Sometimes the given features are like this. These are the given features. But the good features, just by changing the basis maybe give you some good features. If you want only one feature for this data, maybe that one feature is this feature. Project all the data onto this one and then take that one feature. If you want only one feature, right? So there is something called as principal component analysis, which is going to tell us what are the good features. That means it is going to create a basis for this, and these things are well known nowadays. So there are unsupervised means unlabeled data is given. We want to learn the structure present in the data. That means we are given a pool of pictures. The pictures may be having cat pictures and dog pictures. Both are given to the child, and we give a new picture. The child has to say that this picture belongs to the cluster of pictures which may be cat pictures. So now the child has to first cluster the given pictures as cat pictures and dog pictures, are saying that this is cluster 1, this is cluster 2. Then the child has to say that the given image belongs to this cluster. So unsupervised important problem is to find the clustering structure. That is, because it is unlabeled, we are not given the labels. To give a label is the important problem. There are various ways in which the clustering can be done. K-means is there, and hierarchical clustering is there, density based clustering is there. So these are several things are there. Okay, so I think I took more than the given time. So any one or two quick questions can be asked me if you are having any questions.
Good morning, sir. Sir, could you throw light on how this session is going to be? Like, what would be the would we be implementing algorithms from scratch? Would we be using any APIs? How would the implementation process be like?
No, this is basically an FDP. We are not going to cover everything related to any field here. We are going to give you some techniques. Once you know the techniques, technique is going to cover at some abstract level only. It's not going to cover from the scratch actually. So after that, you have to do your work to learn the technique in detail. In the lab, actually, the lab session is that because some participants are not so thorough with the Python language, so that's why the resource person said that she will give some lecture, initial lecture on introduction to Python. Then she will go into this deep learning toolboxes. Okay, so there mostly she is going to give a demo kind of thing. Okay, and we are going to cover some basic Now are you able to hear? Yeah. So with one machine I got one problem. So if your question is on lab, the lab is only to give you a demo kind of thing. Mostly we will not ask you any exercises to be solved in the lab. Okay, so this is more or less at an abstract level. We are going to cover various aspects of natural language processing related to deep learning. Okay, is
Okay.
yeah, please. Is this answering your question or not?
Yes, sir. Yes, sir. Yes. Thank you.
So any other question? If there are no more questions, then let us go to the next session now immediately. Uh, the next session is Introduction to Deep Learning, and this session is given by my colleague, Dr.
Sir, one question.
Yeah,
How are you maintaining the attendance, sir? Attendance link will be sent or you will be recorded sessions will be considered?
attendance. This is a good question actually. Now the meet session will automatically capture the attendance for
Yes, sir.
our classes that was getting captured actually. Let me see today if the attendance is captured, then it's okay. Otherwise, I will ask you to enter your name or something in the chat box.
Sir, otherwise you can share some Google Forms or something like that we can fill and send. That's also one more option.
Yeah, that also one can do. And yeah, see there are rules are there. 80% attendance, 60%. But you know that, right? We can be a bit
Yes,
lenient
sir.
on these rules, but provided within some bounds, we can be lenient. Okay. And enjoy this FDP. Don't worry about your exams and all these things. I will see that your assessment test is going to be easy.
Yes, sir. Thank you.
Just listen and feel what is there in the domain. Okay.
Yes, sir. Thank you.
So now let me introduce my colleague, Dr. Sivaram Dubey, and he did his PhD from Indian Institute of Information Technology, Allahabad in 2016. He is one of the pioneering persons in computer vision group at the IIIT Sri City. Before joining, he was a project officer here at IIT Madras. He was a project officer. He was a recipient of several awards, including Indo Taiwan Joint Research Grant uh, from the government of India, and also he is recipient of Best PhD award for his PhD uh, in the PhD symposium at IIITM Gwalior, and also he got early career research award from the SED, and NVIDIA GPU grant he got 2 times, and he received outstanding reviewer award from some reputed journals like Information Fusion. Okay, and he published several best paper awards also he got. He is one of the good researchers at the IIIT Sri City, and he is an active person in the computer vision group. So now, let me hand over this to Dr. Sivaram Dubey.
Okay, sir. Thank you very much, sir, for introducing me and giving a chance to have a session in this FDP, and also introducing these participants with respect to the basic fundamentals of machine learning and how this machine learning is actually evolving in terms of the deep learning. So in this session, basically what we are going to have a discussion on some aspects of the deep learning, and we will also start from the machine learning, but we will not devote much time in machine learning topics. We will quickly come to the deep learning things. So just let me to share my screen now. So first of all, a very good morning to all of you and welcome to this session in this FDP, that is an introduction on deep learning. So I hope that I am audible properly and my screen is visible to everyone.
Yes.
So, if you see about just a quick introduction about IIITS City, even you have already introduced, but this is a kind of a research-led institute where the research is basically at utmost priority. Most of the faculties, even if you just go through even the faculties profile, you will find that most of the faculties are having even PhDs from abroad, or even having a lot of post-PhD experience from abroad, are very heavily engaged in basically leading the research projects and involved in a lot of research activities, having the research students. In fact, even we are one of the institute where research is also promoted at undergrad level. Even our BTech students also do research. Some top BTech students are given the chance to do the this BTech by honors, basically, that is called the research-led program. And this campus is this is basically the graphical view, so it is under construction. And I suggest all of you just go through once the website of IIITS City, have a look over faculty's profile, what kind of research people are doing. And there is a lot of activities happening in artificial intelligence area. Even BTech program is going on here in artificial intelligence as a minor. And even MTech in artificial intelligence and machine learning is also started. And basically the first batch is already enrolled and classes have been started and it's going on. There are research groups also. For example, we have very strong computer vision and machine learning research group where we have many PhD students working in these areas, solving some problems. Even funded projects are there, people are solving. So basically, a lot of research is happening in deep learning area, and some applications like basically this sometimes this problem or computer vision problem, image processing problem, or natural language processing related problem. So all these aspects are let's say heavily being basically research being conducted. So this is just about this IIITS City and what kind of culture is being grown up here. And that's why this institute is a little bit different as compared to other institutes in India. So for this talk, a quick outline is we will just have a basics of this machine learning, just a quick look, and then we will go through this introduction of deep learning and some aspects related to deep learning, like some activation functions, optimizers, some regularization methods, tuning, and some basic architectures, basically like convolutional or recurrent. And I will try to have the application in mind that is related to natural language processing. Though I belong to computer vision area, but still in my talk here, I try to restrict myself to NLP related problems. So if you see machine learning, so machine learning basically is a field of computer science that gives computers the ability to learn without being explicitly programmed. Now, what is meaning of without being explicitly programmed? Means suppose if computer has to take some decision at the test time, then at the test time we are not going to explicitly program that, okay, if you are doing like this, then you are going to basically give this decision. Rather, we are going to generate a learned model, and that learned model will be generated from the data. So basically, we will have the data. From the data, our machine learning algorithm is going to learn the characteristic of the data, and based on that learning, that representation or the learning mechanism at the testing time or at the prediction time, basically we will use that learned information as well as this new data in order to have the prediction at the test time. So it means that there is something that some intelligence has to come here that can basically explore the given data, and that's generally termed as the training data. So whatever training data we have, some characteristic has to be explored, and then that characteristic has to be used, or that basically the knowledge has to be gained from that label or that data that we have, and that knowledge has to be utilized at the test time whenever we are going to have basically do the let's say kind of a prediction or classification. It depends upon the problem, what problem we are trying to solve. So the knowledge that we are gaining during the training time, that is going to be used at the test time to do some task. But when we are saying that we have to gain the knowledge from the data, then this is very vague word, because Why it is very vague word? Because how we can basically find out the knowledge from the data. So there are different types of the learning. So for example, there is a supervised learning, there is unsupervised learning, there is reinforcement learning. So in this session, though, we are going to restrict ourselves to the supervised learning, but we can have an understanding that what is the difference between these learning types. So supervised is the learning techniques where basically we have the labeled training data. So what is the meaning of labeled training data? That suppose if we have a sample of the data, then what is our expectation from the data is also known. So for example, if we talk about the classification, suppose if we say that if this is the text document that we have, then this text document is belonging to class A. Suppose some other text document is belonging to class B. So suppose if this class information is also given, then at the training time itself, we can utilize that class information, or we can utilize that what is our expectation that we can utilize during the training time, and that is basically called the supervised learning. Whereas in case of unsupervised learning, we do not know that what is our final expectation, or basically we do not know that what is the labels. So we have to find out the characteristic of the data from by basically computing the properties of the data, that how data is related to each other, what kind of similarities or dissimilarities are present in the data. So there will be different strategies basically dealing with such type of let's say aspects. Another type of learning mechanism is this reinforcement learning, and reinforcement learning is something where basically the learning is happening by learning from the mistakes. That suppose if you're the model that you are trying to train, if suppose if some mistake is happening, then you have the feedback system or reward system. Based on that, basically you are giving some reward, or you are basically giving the feedback, and that feedback is going to used in such a way such that next time the model should not repeat the similar mistake. So basically we're not going to have a more emphasis on these different types of learning. Now let's just have this supervised learning, and let's try to understand through the supervised learning that how we can basically now go forward to this deep learning part. But before going to deep learning, let's have a quick look over the classical ML classifiers. So now basically we are restricting our discussion to the supervised. Then in nearest neighbor classifier is one of the traditional classifier, and in this particular classifier basically we have all training data available with us. So now if you see what is the meaning of this circle here, so this circle is representing n-dimensional data, and because it is represented in n-dimensional world, so that's why basically it is represented with 1 point here. So if we have any test sample, then test sample is basically going to belong to that particular training, that particular class, basically with respect to which we are going to have the smallest distance. If we compute the distance between our similarity or dissimilarity between this test sample and all these training samples, then we can find out that particular sample which is the nearest to this sample in terms of the distance, and then whatever is the label of that sample can be transferred as the label of this test sample. So this is one of the very basic classifier. But what is the major drawback of this classifier? That we have to memorize all the training data always, and that is going to be very consuming process. Suppose if you are dealing with in current days, where suppose your data set has 10 million of images or 10 million of documents, and suppose if we have to memorize all these documents always, and you have to compare whenever a test document is coming, you have to compare with all 10 billion of documents, then it is going to be a very time consuming process. So that's why this nearest neighbor classifier might not be suitable in the recent let's say time. K nearest neighbor classifier is the extension where we will find out basically then let's say K number of nearest neighbors, and we will perform the majority voting in the class labels. Based on that, we can find out the classes. And there is a linear classifier. This linear classifier basically is very important here to understand, because even in the recent days also, even deep learning, there is a hype of deep learning, but deep learning is somehow, this is also very much related to this type of classification techniques, because when we will move forward and we will see deep learning, again we will find very similar expressions like this W dot X plus B. So let's try to understand that what is the meaning of this w dot x plus b here. So x is nothing but x is the data, and data is represented, let's say in suppose if the dimensionality of the data is d, then basically it is being represented in a d-dimensional space. So this x is the data, and what is this w? So w is nothing but w is the parameter. And what is that parameter? In order to understand that parameter, suppose if we just simplify this problem here, and if I say that, let's say you have to do the classification of the points. Even let's not consider this as the data. Let's first consider as the simple points. Suppose these points are of one type and these points are of another type. And if I say that, suppose can you find out a line that can distinguish these two distribution of points, then we can say very easily that, okay, if we have this line, then whatever is the left side of this line can belong to class 1, and whatever is the right side of this line can belong to class 2. Then it seems very easy, and we know that what is the equation of the line, and equation of the line can also be represented in terms of the w dot x plus b, because we know that whatever is the equation of line, even if you have the equation of line like y is equals to mx plus c, then we can say that m is here w, and that we can find out that what is the value of m, and that c, whatever is there in y is equals to mx plus c, that c is nothing but b here. And the same thing, if we want to extend it for the multi-dimensional data, multi-dimensional means, let's say, if it is a point, then it is a two-dimensional data. But suppose if this is a d-dimensional data, and we can think this diagram in a d-dimensional space, then this line that was in a two-dimensional space will become now a hyperplane in d-dimensional space. So now this is going to become a hyperplane. And suppose, let's say, if it is a hyperplane, then what will be the equation of the hyperplane? So now we can represent the equation of the hyperplane in terms of the matrix multiplication. So now we can say that we can write it w dot x plus b, because this x is n-dimensional, let's say d-dimensional, then this w is also going to have d number of values. So suppose if w is also going to have d number of values, then this w dot x is basically representing the dot product, and this, what is the value of this w, that is not known. So, and that's what is the basically the whole problem of the machine learning, is to find out that what is the value of this w. If we can find out better value of this w, then our problem will be solved. But if our data is linearly separable, if you see in this particular case, data is linearly separable, means we can have a hyperplane that can basically distinguish the data distribution very accurately without any error. But suppose if data is not linearly separable, let's say if some red ones are at the left side also, some blue ones are at the right side also, in that case data is not linearly separable. Then it is not possible. Then it is not possible to come up with such a hyperplane or line that can basically divide the data into two parts without any error. That is not possible. So in that particular case, error will be generated, and that is called the misclassification error. And our aim will be to basically minimize that misclassification error. Or there is another strategy which is called basically the transformation of the data. So now, if data is, suppose if it is not linearly separable in the original space or in the data space, then can we project the data in some other, in some higher order space where it can be linearly separable? Then actually we can solve the problem in the higher order space. We can have our classifier into the higher order space, or basically the classifier we can implement not on the original data, rather on the representation of the data. And what is the expectation here? The representation of the data should be very much linearly separable. It means that now basically it is going to lead to some multi-step process where if data is not linearly separable, then we can project the data in some other space, which is basically called the representation. And that is basically the whole area that was earlier referred as a feature extraction. Basically from the data, we can now extract the features, or basically that is the representation of the data. And in representation of the data in that space, it is possible that basically The representation might be even better separable in terms of the linearity, then even we can find out a better classifier in that space. So that's why if you see in a classical machine learning approach, most of the time you will find that this is a two-step process where first you are extracting the features, which is nothing but projecting your data in some other space where it might be linearly separable, or where it is easier to solve or easier to apply the classifier. And that is basically called the feature extraction. And then the second step is going to basically apply the classifier on in that space. And basically that is a two-step process. But this is, if you see, this is a two-class problem. What will happen if we have the multiple classes? Because most of the time, in reality, we are going to end up with the multiple classes. So again, the same thing that w dot x plus b is also going to work even in case of the multiple classes. Now, in case of multiple classes, this w is going to be repeated. It's going to be repeated how many number of times, that is related to how many number of classes we have. For example, suppose if we have 3 classes, now we can have 3w. So for example, here you can see the first row of the w is basically the value of w that is corresponding to class 1. The second row of the w is corresponding to class 2. The third row of w is corresponding to class 3. Or in other words, we can say that the dimension of the w is now going to be, C cross D, where C is the number of rows, basically the number of classes, and D is the dimensionality of the data. If we are applying on the raw data, then it is dimensionality of the raw data. If we are applying on the feature representation of the data, then it is the dimensionality of that feature. So in this particular example here, this picture is basically converted into some feature space, and just a simple strategy is followed by stretching it out. We are just assuming that suppose this has the 4 features, let's say these 4 features for this particular input, then the dimensionality of this W here is 3 cross 4, where 3 is the 3 classes, which is respect to the cat, dog, and sheep, and these 4 columns are corresponding to the dimensionality because we have 4-dimensional data. And we are going to have one B value for each of the W, or for each of the classes. For, let's say, for first class cat, we have the value of B is 1.1. For the second class dog, we have the value 3.2. So like that we are going to have. So what is going to happen here now? So now if you are going to do this, let's say this, if you multiply this matrix W with Xi, and if you just add B, then we are going to end up with another matrix, let's say, and that is going to give us the class score. So now we can think like this, that in order to get the value, or in order to get the class score for the cat category, what values of W and B are responsible? Then if this is the first value here, then only the first row of W and first value of B, they are responsible to get this value. So it means that whatever class scores are generated here, it is generated based on this, the first row of W and first value of B. So now we can say that basically the first row of W is a classifier. First row of W is a classifier for the category cat. Second row of W is a classifier for the category dog. Third row of W is a classifier for the category sheep. And now at present, and in present example here, suppose if the value of W, if the values of W is this, if all these elements having the values like this, then, and if the input is like this, then at present this input image is going to give us the class scores like this. And now we can say that this basically this can be classified as a dog because it is giving the highest class score for the dog category. But now, so now this is basically extension to the multiple classes. But now one question comes here that if you see in this particular example, this is a misclassification because we know that this is a cat and it should give the highest score for the cat, but actually it is giving highest score for the dog. It means that it is not correct. If it is not correct, then where is the problem? Problem is not here because now we are assuming this one as the feature. For this feature, we have to find out the right set of the values of W such that for most of the example, it should give the highest class score for the correct class. So it means that it means that the present value of W is not right, is not good. And that's what is the basically the whole machine learning area here, where we have to find out, even in the deep learning also we are going to do the same thing, that if we have to find out the right set of the values, and this is basically called the parameters. So if we can find out this right set of values, then we can generate the highest class score for the corresponding correct class, and then basically our classifier will work well. So now again question comes that how to find out the values of W, and basically how to start with. So that is basically going to have a kind of a different tricks or different kind of approaches. And suppose if we are going to basically work, if you're going to discuss the deep learning part, then in deep learning part, this W is basically what we are going to do. We are going to initialize this W, because we, from where to start, we don't know what should be the initial value of W, we don't know. Then from somewhere we have to start. Then basically we will start with the random values. So we will consider the values of W as a random values. And if we consider the values of W as a random values, then there is a very likely that the class scores that we will get, most of the time it will be because the class scores will be also random. If class scores are going to be the random values, then there is going to be possibility of doing a lot of misclassification. But now suppose if this is the training phase, then during the training phase we are saying that this particular let's say input is belonging to cat category, but my approach are basically when I am doing this W dot X plus B, then for this particular cat I'm not getting the highest score for cat, rather I am getting the highest score for dog. Then because we know that at the training time we know that this has to be cat, but if it is not classified as a cat, then basically this is going to be a misclassification. Then for this misclassification we have to penalize this training, and this penalization is going to happen in terms of the loss function. So it means that if some misclassification is happening, then we have to generate some loss, and that loss has to be minimized. And what we can do, we can try to change the value of W in such a way that next time that misclassification should reduce. And that's what is the basic fundamental of this learning of the parameters, or this learning of these values of W. When we will see for the deep learning, then this updation, this whole part is basically done by some optimizer, which is called gradient descent. We will have a look quickly on that. So now this is basically the fundamental. The same thing is going to be used even in the deep learning also, that we will have the parameters, we will initialize the parameters with the random values, we will get the scores might not be correct, then we will generate the losses that in order to reduce the loss for the coming, let's say the training process, we have to update the value of W. How we should update the value of W such that next time it should do better, and that's what we are going to discuss. This is another very common techniques, which is called support vector machine. We are not going to discuss more here, but support vector machine also tries to find out the hyperplanes, and because there might be infinite number of hyperplanes that can separate two distributions, then it tries to find out a hyperplane that can give us the maximum margin, and the margin is basically defined like this. So if W is a parameter, then we have to maximize the value of this 2 divided by norm of W. And basically, if we just do that, then we can find out the equation of this hyperplane, and we can also find out the support vectors. Support vectors are nothing which is basically which is on this upper and lower hyperplanes. So we are not going to discuss in deep for this support vector machine, but if someone is interested, you can explore it further. So now let's have a look over this ML versus deep learning. So as we discussed that in machine learning, even in the previous session of machine learning also, it was emphasized that in machine learning, basically, this is a multi-step process where first you are representing your data using some feature extraction technique, which is nothing but projecting your data in some higher order space where we can solve the problem, or we can do the classification in a better way, or in a more linearly let's say separable way. But what is happening in deep learning? in deep learning, basically the now what is the drawback of that machine learning pipeline? In the machine learning pipeline, if you see, first we are describing the data using some feature extraction. And what is the need of describing the data? Because in practice, most of the time the data which is available is not linearly separable, then we cannot get very good performance using directly applying machine learning algorithms on the raw data. So that's why we need to transform the data, and for the transformation we are basically doing some feature extraction. And that feature extraction basically is generally done manually. What is the meaning of manually? That which feature to extract for this, which feature to extract for this. It is sometimes is going to be the problem dependent, as well as what is the even sometimes it is going to be the data dependent also, that what kind of data we have. For example, suppose if we have an image, and suppose if we are talking about the face, and suppose if we have to do the face recognition, then the features that we might be looking for, that okay, what are the how these eyes are looking, or how this nose are looking, how the mouth is looking. So we can basically focus over such type of features. Suppose you are doing, let's say in NLP, you are doing the sentiment classification, then you can look for the features in the sentiment classification, that what kind of words are being used, that word is having the negative meaning or positive meaning. If you combine with the multiple words, then what could be the meaning? So suppose if we just do the feature extraction based on such kind of things, then basically that is going to be called the hand engineering the features, because we are not doing it with the learning, rather we are doing it by our human let's say our human intervention, that we are thinking that in order to solve this problem, such type of features might be better. Then people are extracting that feature, and ultimately that feature is going to be used with machine learning algorithms to do the classification or some other task. But now what is happening when we are doing this hand engineering feature extraction, then actually it is basically because this is hand engineered, we cannot think many perspectives, or even the features that we are extracting might be giving good result only a particular scenario. But if you just change the scenario, if you just change the data, then it might not give the correct result, or even we might not be able to even extract all the important features, because if you are extracting some features, then there might be some features that we are not extracting, that is also important in order to solve that problem. So that's why most of the time, and in fact that is going to be more problematic if we have to deal with a huge amount of data. Then in huge amount of data we can find a lot of variability. In that particular case, identifying manually that which feature is better, which feature is not better, is going to be very basically difficult task, and it needs a lot of domain specific knowledge. So that's what is the basically this objective of deep learning, is to get rid of this manual extraction of features. Rather, let's feed the input as the raw values, and let's basically the let's the learning algorithm itself to find out that which feature is important, and let's learn the feature automatically from the data, and ultimately do the classification or whatever task for which we are going to apply the deep learning. So now if you see in the classical, this machine learning here, first we are extracting the features, then we are applying the machine learning. But now in deep learning, these two things are going to be combined in a single one, a single step. And in the single step, basically, the initial layers of the deep learning might be devoting more efforts to find out the important features. And ultimately, in the last layer, we can have this classifiers, basically, and that can do the classification on top of the. And basically, you can also think like this, that this deep learning also is going to do some very similar task, that whatever raw input you have, it is going to project your raw input in some feature space or in some abstract level space where it is going to be linearly separable, so that classifier can do well. And what should be that feature space? It is learning automatically. So basically, this is a machine learning subfield of learning representation of the data. We are going to represent the data, but the representation is going to learn automatically. And exceptionally effective at learning patterns. It is basically performing exceptionally good. And deep learning algorithms attempt to learn multiple labels of representation. This is another important aspect here, that because in deep learning we are going to have we are going to have several layers, then the representation of these features are going to happen in an hierarchical fashion. So basically what will happen, the initial layers will focus more on the primitive features or important or basic features, and later layers will use the extracted primitive features to build up more and more abstract features. So if you go from the initial layers to the late layers or deep layers, then the abstraction level of the features will increase, and ultimately once you reach to the last layer, then you will get the most abstracted features. And basically abstracted feature means it is going to be more towards linearly separable property, and in that particular case our classifier can do very well. So, and another important thing, using deep learning, we can deal with a huge amount of data, and in vice versa. To get the good performance using deep learning, we need huge amount of data. So even in deep learning also, if you see, this is basically nothing but this is a neural network. And I hope that all of you are aware with the neural network. So even this neural network was existing long ago. Even if you remember, even if you can find out also that during 1990s, a lot of work was happening in neural network area. But what happened actually at that time, even there was neural network and people were working in the neural network area, but people could not get good performance using neural network. And what was the key factor restricting success of the neural network in early days was basically due to the limitation of the computational resources and due to the limitation on the availability of the huge amount of data. But now if you see in recent past, a lot of progress has happened due to this GPU based accelerated computing. Now we can do let's say a lot of computation very quickly, and a lot of data sets, a huge volume of data sets has been gathered in the recent past. If you see the era of this 2000 to basically 2010, at that time a lot of efforts have been devoted to gather a huge amount of data sets, and that has basically pushed to the success of this deep learning, where due to the availability of huge amount of data and due to the facilitation of the let's say this parallel computing or high-end computing using CPUs, nowadays basically this deep learning is able to basically perform very good. And the same thing was not possible some time back due to these lag points. So now if you see why deep learning is useful, so basically manually, if you are manually designing the features, sometimes it may be over-specified, sometimes it may be under-specified, it may be incomplete, or even it may take a long time to design, even to think that what should be the bad features are good features. Whereas the learned features are easy to adopt, it can learn very easily automatically from the data, and it provides a lot of flexibility. Even nowadays, if there is a transfer learning, and that is the flexibility of the deep learning, that already learned model we can use just to be fine-tuned, and we can use for some other problem. We do not have to learn from the scratch. And it is universal learnable framework for representing universal means it can be used even for the world or even for the visual data, or if you have any type of multimedia data nowadays, then basically we can apply the deep learning on that type of data, and can learn both in unsupervised and supervised mode. We are only seeing supervised, but even there are methods like called autoencoder or generative adversarial networks. They are also working very well even in case of the supervised learning of the data using deep learning, and very effective for end-to-end joint system learning. Means now we do not need to step. You just have the data, you just have a network deep learning model, you are simply learning and you are having the final output. There is no multi-step here, utilizing large amount of training data. And now if you see the growth and even the interest in machine learning, even you can see here, this graph is basically showing that on and around after 2010, a lot of interest has been generated in machine learning area, and basically due to this deep learning. And first it was started in speech, then in vision, basically it was started in 2012, and even now in NLP also it is very heavily being used, this deep learning based techniques. So again, if you see, this is the state of the art. For example, in deep learning in speech recognition, if you see on and around this 2010 or around 2010, this is the error here. The error is drastically got decreased. This means the performance of the model is drastically increased. Even if you see from 2000 to 2010 roughly, this was the era where people were basically designing different features and using a lot of classifiers, but there is no major improvement. Suppose someone is getting performance 86%, another one is getting performance 86.2%. So means improvement was there in the fractions. There was no much improvement. But when this deep learning became successful around 2010, then you can see in the error there is a huge drop. And in fact now basically not just even in the speech recognition, even the same thing has happened even in case of the computer vision also. There is something called ImageNet challenge, which can be also thought as a computer vision World Cup, where basically this is kind of an image recognition problem where basically it is being done on plenty of data. So up to 2011, the models were basically the hand-engineered models that were basically winning this one. But in 2012, the first model came that basically owned this ImageNet challenge, that is called the AICTE model, and it is also the first convolutional neural network model that came in the present era. And basically it again dropped the error drastically. If you see the error that was let's say around this 25% or something got reduced to somewhere 17%. And after that, even a lot of improvement has happened in this deep learning area, basically in convolutional neural network. And in fact, nowadays, even we have networks like residual network, even it is surpassing the human level performance. So the human level performance on this ImageNet is also measured, and the performance of these networks are even better than the human level performance. So that's what is the improvement, or that what is the basically kind of a huge progress has happened in this deep learning area. And mostly it was started around 2010, and we are discussing just after 1 decade the growth in this deep learning area. And there is a huge amount of growth. And in fact, even in deep learning also, whatever done even around 2010 or 12, even nowadays people are saying that it is obsolete, because now this world is changing very fast. And even daily we are getting a lot of research papers are coming in this area, and they are even pushing all these boundaries. So several big improvements even in the recent years in NLP, which is basically some problems like machine translation, where if we have to translate from one language to another language, sentiment analysis, suppose if we have a sentence, if you have to, let's say, find out what kind of sentiment it is giving, some dialogue agents, question answering, even question answering is extended to even the vision also, where we have the visual question answering, text classification. And so basically it is going to leverage different labels of representation, either word labels, character labels, at the syntax labels or semantics labels. So at the different labels, basically the representation at different labels are going to be leveraged by these deep learning models in order to do these type of tasks in the NLP area. So now let's dive a little bit into this neural network and some more this technical part of this deep learning. So I think all of you should aware that this neural network is nothing but this is basically just a combination of a lot of neurons, and these are artificial neurons, and these neurons are doing some computation. And for example, suppose let's say these are inputs. So this input means it is having, let's say, 3 data values, and now this is one neuron, and this is the hidden layer. Let's say this is the output layer. So this neuron will get the input from all of the nodes in its previous layer, and it will have some weights here, and these weights will get multiplied with this input, and ultimately we will have summation, and then there is a bias term. That bias term is going to be added, and on top of that we will have a learning. On top of that we will have an activation function, and that activation function will basically transform whatever output we are getting in some other form, and that is basically also called the non-linearity. And the same thing is going to happen even at the output layer also, and ultimately this is going to give us the final output. Suppose if we little bit go deeper here, then suppose if you have to find out what should be the dimensionality of this W, then basically we can find out the dimensionality of W based on how many number of nodes we have in the previous layer and how many number of nodes we have in the current layer. So now we can have some And it also depends upon the policy. Do we have the shared policy or not? If it is shared policy, then the same W that is used for one neuron can be also used for other neurons. But if it is not the shared policy, then we can have the different Ws. Then the number of parameters is going to be defined basically based on that, how many number of neurons we have, as well as what is our policy. We have shared policy or we have non-shared policy. So, but this W is the parameter here. Initially, again, this is going to be the same thing. We are again going to compute this W dot X plus B. And that is going to happen even for all neurons. We are going to compute this W dot X plus B, where this W is basically the parameters, X is the input that we are getting from the previous layer, and B is the biasness, that is also a parameter. And on top of that, we are going to have some activation function. So that's why when I was discussing a little bit about machine learning, I mentioned that this W dot X B plus is very important because it is going to be repeated in the deep learning. Now, if you see there, we are doing the W dot X plus B once, but now in deep learning, we are going to do this W dot X plus B multiple times. In fact, for each neuron, we are going to do this W dot X plus B. So it means that even each neuron, we can think like a classifier. Basically, it is getting some input and transforming it into some output. And once we are having this final one, then this final one is going to give us the classes score corresponding to the classes. So in this example, we can assume that we have two classes, and these two neurons are going to basically give us the classes scores for those two classes. And what is the importance of this hidden layer? Basically, if we have more and more hidden layers, then our neural network will become deeper. And suppose if the number of hidden layers are many, then that network will be called as a deep neural network. And once number of hidden layers are more, and if it is a deep neural network, then that is also going to be termed as a deep learning based model. Because if we have 10 hidden layers like this, then the initial hidden layers will learn, basically this W will be adjusted in such a way that it should extract the primitive features from the input, and then the other layers will make use of the extracted features in order to learn even more abstract level feature. So that's what is going to happen in this neural network. We can just have a quick demo here for this working of this neural network. It should not take much time. So just for example, this is a very well-known this repo here. Suppose if we have, let's say, some data. So let's say we have a data, let's say, of two classes, and there is no noise here. It is separable. Even if you have a circle here, it is well separable. Suppose if I add some noise here. So now if you see, after adding this noise, some red dots even is interleaved with this one, even with the blue one also. And here, this is actually showing that this is the input, this is the final output, and this is basically 4 neurons. Even we can increase the number of hidden layers. Suppose now if you are going to have 2 hidden layers, we can increase the number of neurons in the hidden layers also. So now one question comes that, what is the importance of these number of hidden layers as well as the number of neurons in a layer? So basically, if we are going to have more and more neurons in our network, then it is going to increase the capability of our network in order to even learn a more complex data. Because all these neurons are also going to be equipped with something called the non-linearity, and that non-linearity, because it is going to transform its input in a non-linear fashion to the as the output for the another layer, then basically that non-linearity is going to lead to the projection of our input data in some other space where it is going to be at a more abstract level. And if we have more and more layers, then basically the capability of our network is going to be increased. In fact, still there is no hard and fast rule how many number of layers, how many number of neurons, but this is also one of the research area where one of our PhD students is working in that area. He's trying to even find out that what should be let's say what should be the optimal number of layers, what should be the optimal number of neurons. If we know a data set, if we know a complexity of the data set, then can we measure it? Can we find out, or can we have some intuition that we can utilize when we are going to pick the number of neurons, or even we are going to pick the number of layers? So suppose if we are going to run this particular example here, then what it is going to happen, then basically the W values that we are going to have that is associated with all these neurons will be initialized with the random values, and then we are going to basically apply this gradient descent. Using gradient descent, the value of W is going to be updated based on the loss that we are going to generate, and the loss that will be generated here, we can basically very simply we can generate the cross entropy loss, because cross entropy loss is one of the loss that is generally used if you are doing the classification of these two classes. So suppose if you are running this particular one, so here you can see So this one is showing that this training loss, initially the loss was more, but then this parameters was basically updated in such a way that the loss got decreased, and at the same time this test loss also got decreased. And even if you see now, if you just keep doing this training, then it will try to adjust this boundary between these two classes in such a way that all reds should be one side and all blue should be another side. And in fact, if you see even why these two reds are basically not this part of this, because now this is basically trying to adjustment of this boundary such that it should represent exactly what we are providing as the training data. And if we just keep training for a longer time, then sometimes it will also lead to the overfitting, where this boundary, this is called basically the boundary between these classes, will be learned in such a way that it can exactly overfit the training data, such that the error during training will be very less. But at the same time, if we are going to use and this is the learned model, so basically this boundary, if we use at the test time, then many times there is a possibility that for the real test data it may do misclassification, and that is basically called the overfitting of the training data. So I'm just stopping this particular thing here, and let's continue our discussion on this neural network. So if I have to count the number of neurons, so number of neurons at this layer, number of neurons is 4, at this layer number of neurons is 2. If you have to count that how many number of weights are there, then if you count this W, then these all four are having 3 weight values, then 4 into 3. All these 2 are having 4 weight values, then 4 into 2. And all these 4 plus 2 neurons are having 1 bias term, so total 6 biases. So this particular example is having the 26 learnable parameters, and that is the W values. So these are called the weights. These activation functions, we will come to this in a bit. And now next question comes that how do we train? And that is the most important thing, that how basically we can do this initialization and how we can perform this training. This is just loose inspiration that this artificial neuron is very much related to the human neurons. It is not exactly similar because it's still exactly how human neuron works. It is still not fully explored. Yeah, but in human neurons also, basically a neuron even this biological neuron also gets the input from other neurons and do some processing, and then basically perform some firing and provide the inputs to some other neurons. And basically a very similar mechanism is followed here also, that we are getting the input from some other neurons, and then we are doing some processing here and giving the output to some other neurons. But the processing that we are doing is not same as the processing done in the biological neuron, because what exact processing is done in biological neuron is still unexplored. So now, how we will perform the training of such a deep neural network? So when we are going to perform the training of such a deep neural network, then first thing what we have to do, we have to first take some sample of the data, and which is called a batch of the data, because we cannot perform basically this training of the data by computing all data all together, because then it will require a lot of memory, and maybe that much memory we will not have for the processing. So that's why we will basically we will consider a batch of data, and then we will process a forward pass. Forward pass means if that is the input, and if W values are initialized randomly, and then what should be the final output that we will get. And once we will get the final output, then if this is going to be a supervised problem, then we also know that what is the output expected, and if we are getting some other output, then we will generate basically the error, and that error generation is basically called that is based on basically the objective function, or that is called the cost function. That what is our objective function, using that we are going to generate the error. And once we got the error, we have to backpropagate the error. Now this backpropagation will happen from the lateral layer to the initial layer, and the backpropagation of error means what? Basically, we are going to update the W. We are going to update the value of the parameter in such a way that next time it should perform better. And how we can update the W so that next time it should perform better, and that we can basically find out from the fact that we can compute the gradient. And if you can compute the gradient of the loss, basically the objective function. So it seems there is some noise here.
Yeah.
Okay, sorry.
Yeah. Now, I think now it will be all right.
Yeah, sir. I will just come to that. Yeah. So basically, there are different optimizers here. They are based on this gradient descent strategy. In that strategy, basically, we know that suppose if I give you a function, let's say if I give you a function fx is equals to x square, and if I say you, let's say if x is equals to 4. If I say you if x is equals to 4, then x square is going to give you the 16. Now, if I say you that if I change this x with some delta amount, now, if I say that if I change this x, let's say 4 plus some delta amount or 4 minus some delta amount, in which case this x square is going to be reduced. So this problem we can solve very easily because we know the concept of this gradient. So because this is going to be dependent upon this slope, so what is going to happen in that particular case? Suppose if this is fx is equals to x square, if you compute the gradient, then gradient is going to come basically the derivative that is going to come 2x. It means that what is the meaning of 2x? The meaning of 2x is that if we make some change in the x, then what is going to be the effect? The effect is going to be basically our x square is going to be increased. So that particular criteria, that particular fact we can basically use in this gradient descent optimization, that now for any parameter we can find out that what is the gradient for that parameter, and that we can find out for the loss function. And once we know that how loss function is dependent upon this parameter, if we increase the value of this parameter, what will be the impact in the loss function? If we decrease the value of this parameter, what will be the impact in the loss function? Based on that, actually we can make our choice, and that we can find out very easily from the gradient. So because if you find out the gradient, and if we just update our value in the direction of the gradient, then in that particular case the objective function will be basically increased. The value of objective function will increase. So, but our aim is here to minimize the objective function. Then we will not update in the direction of the gradient. Rather, we will update the parameter in the opposite direction of the gradient. So, what is going to happen during the back propagation? So, back propagation is the name basically, that is back propagation of the error. So, and in back propagation, what is going to happen? These parameters are going to be updated in the reverse direction of the gradient for that parameter. And if you see here, there are different versions of gradient descent, like this vanilla version where we are considering the entire data set together, mini batch where we are considering one batch of data, and stochastic is generally used basically when we are going to use a single example at a time. But what is going to happen? We will get, generally in most of the cases, we will generally work on the batch of the data. For a batch of the data, we will extract the batch of the data. Then we will find out the gradient for that batch of the data. And then then all the weights are going to be updated like this. The weights, what is the current weight value, minus there is a step size, means we are updating in the opposite direction of the gradient, but with what step we should let's say go ahead, and that is basically called the learning rate or step size, and multiplied with that what gradient we have computed. So if this is the gradient, we will update in the negative direction. That's why this is the minus here. So this is going to become weight is equals to weight minus step size into the gradient, and that is going to basically apply for all these parameters. But then one question comes, and even it should come in everyone's mind, that suppose if we have to update the parameters, in the opposite direction of the gradient. Suppose if we have a function like this, fx is equals to x square, it is very easy to find out the gradient. But suppose if we have a hierarchical function, means let's say if we have a multiple layers, then that is basically going to constitute multiple functions, or in a hierarchy of functions. In that particular case, how we can compute the gradient, and that is also very easy to compute, and that is called basically the chain rule. So what we can do, suppose if you have a function like this, that suppose if fx is going to be dependent upon gx, and then first we can compute the gradient for let's say fx by considering this let's say gx as one of the parameter. Then we can compute the gradient for gx with respect to x, and we can apply the chain rule. Just let's have a look quickly over this. What is the meaning of this chain rule? So first of all, this is interpretation of the gradient. All of us know that we can write the gradient like this. That suppose if you have to compute the first order derivative, then basically this can be represented that what is the change is going to happen if we are going to basically update with very small fraction, or if the step size here or step is here that is limit to 0, in that particular case what is the amount of change that is basically going to give us this basically the gradient. So suppose if we have fxy is equals to x plus y, suppose if this is a function, and if you have to find out the basically the gradient of this f with respect to x, then we can simply do this partial differentiation, and if you do the partial differentiation, then it is going to come as 1. Similarly, if you compute the derivative of f with respect to y, the partial derivative, then it is going to come 1. Suppose if you have a function like this multiplicative, fxy is equals to xy, if you compute del f by del x, then because we know that if we have to compute del f by del x, then this is going to be y. And if you compute del f by del y, it is going to be x. So this is basically the partial differentiation of this multiplicative variables. Similarly, suppose if we have now, we have done a lot of this differentiation basically for this such type of functions. But what will happen if we have a little bit complex function, like if you have a max function? Suppose our f is the max of x comma y, and if we have to compute that what should be the derivative of f with respect to x, what should be the derivative of f with respect to y. So in that particular scenario, basically what can be done here? So now we have to rely on the value of x and y, that if x is greater than y, then basically max is going to return x. Then in that particular scenario, this derivative will become 1 for x and 0 for y. So this is going to become 1 if x is greater than or equals to y, and this is going to become 1 if y is greater than or equals to x. So basically, if this is true, then 1 and 1 will be multiplied, then it will become 1. If this is false, then false and 1 will be multiplied, and ultimately it will become 0. So that's how actually we can compute the gradient of these very smaller functions. Now coming to the compound expression, and that's what is the actual scenario that is happening in deep learning, because in deep learning we have this hierarchy of layers. Then hierarchy of layers are actually leading to a very compound expression or a very complex expression. So if we have such a complex expression, then what we can do, suppose if we take one example of this compound expression, then suppose if we represent this x plus y with another function. Let's say suppose this x plus y is represented as q, then basically now we can write this f is equals to qz. So now, if I say that f is equals to qz, now I can find out this del f by del q and del f by del z very easily. And if I say that q is equals to x plus y, then I can also find out this del q by del x and del q by del y very easily. And in fact, this del q by del x will become 1, del q by del y will become 1, del f by del q will become z, and del f by del z will become q. That we can find out very easily. But that is not actual thing we have to compute. Actually, we have to compute del f by del x, del f by del y, and del f by del z. Suppose if this x, y, z are the parameters, then this del f by del x, del f by del y, and del f by del z is needed to update the values of that parameter. But because this is a compound expression, and suppose if I already know that what is del f by del q, then can I utilize that information to find out the del f by del x and del f by del y by having this expression q is equals to x plus y, and that is basically can be done using the chain rule. And what is the chain rule here? That suppose if we have to compute del f by del x, then we can write this del f by del x as del f by del q multiplied with del q by del x, because this is at the this is going to be cancelled in an basically if you see what could be basically the equivalent thing, then this del q will get cancelled, and ultimately we will have the equivalent thing like del f by del x. So suppose if del f by del q is already computed in the let's say the previous layer, then that information can be used along with that what is the local gradient. And what is the meaning of local gradient? Local gradient means this del q by del x is the local gradient, and this del f by del q we can think like this. This is the gradient that is available from the previous layer, or basically from the opposite side previous layer, and that can be multiplied in order to get the basically the gradient with respect to the final objective function that we have. The same thing is going to happen here if we just represent this in form of let's say computational graph. then we can say that this x, y, z are the inputs. And if we just do x plus y, then this is going to give us q. If you just do z, if you just we can just do the multiplication of this q plus z, and that is going to give s f. And if you see, very similar in deep learning, what is going to happen, we are going to have some layers here, we are going to have some layers here, we are going to have some layers here. It means that if we have to find out the gradient for any variable in this layer, then we have to dependent upon the gradient that is basically coming from the back from this layer, and what is the local gradient that we will multiply, and that gradient basically will become the final gradient with respect to the final part. So in the forward pass, let's say if these are the input values, then this q is 3 because this is summation, then multiplied, this is minus 12. Now suppose if we are going to back propagate, then this del f by del f is going to be 1. So this is going to be 1 during the back propagation. So what is going to happen here, if you compute del f by del q and del f by del z, so del f by del q is nothing but here that is z, and z is minus 4. So the local gradient here will become minus 4, and this is the running gradient, which is minus 1. So minus 1 and minus 4 will get multiplied, and ultimately we will have minus 4 here. So if we have to compute del f by del z, then del f by del z is nothing but this is q. Then basically the gradient, this 1 will be multiplied with 3, and we will get 3 here. So basically we will have 3 here, we will have minus 4 here, and that is going to be basically the del f by del q. It is, and suppose if you have to compute del f by del x, so now if we already know that what is this del f by del q, then this del f by del x is nothing but del f by del q multiplied with del q by del x, and del q by del x is 1. So basically this minus 4 is going to be simply transferred here, and the same thing is going to happen here also. Similarly, we can have a lot of expressions. I'm not going to discuss a lot of expressions due to the interest of time, but basically, just I will take one more example here. Suppose if the running gradient here is 2, what will be the final gradient for this one with respect to f? If you have to compute the final gradient here, so because this is the max operator, and max of 2 minus 1 is 2, and 2 is passed here, it means that for this line the local gradient is 1. For this line the local gradient is 0, and this is the running gradient. So running gradient will be multiplied in the local gradient. So 2 will be multiplied with 1. So this gradient will be 2. And here 2 will be multiplied with 0. For w, the gradient will become 0 because this w is basically did not contribute in the final output here. Similarly, we can have even any complex function, and we can break down in very smaller, let's say the steps here, and we can find out that this is the forward pass, which is represented by this basically green values, and this is the backward pass, which is represented by these red values. This is basically the gradient here, and this gradient is going to be used to update the parameter. So suppose if w is the parameter, then w is equals to w minus w is equals to w minus learning rate multiplied with the gradient that we have computed for that particular parameter. So that's how it is going to be updated. This is called very simple, very basic, basically stochastic gradient descent based optimization technique. Even there are some improvements in this SGD based techniques also. Even nowadays there is a technique called ATAL, which is very popular, and in practice it is very success in terms of the deep learning. So this is all about this optimization of these deep learning models, where basically we are having these parameters. Using the parameters, we can do the forward pass. For a given input, we can find out the values at the end of each of the layers, and that value will be used as the input by another layer, and ultimately we'll get the final output. And then we will compute the loss that will be computed based on an objective function. An objective function might be different for different problem. For example, suppose if we have a classification, we can have the softmax loss we can consider as the objective function. If you have a regression problem, we can have the MSE, mean square error, we can use as the objective function. So like that, based on the problem as well as basically what type of restrictions we want, based on that we can have a different objective function. But based on that objective function, we can find out the error, and that objective function we are going to minimize. That objective function, the value we are going to minimize by updating the value of w, or by updating the value of each of the parameter in the opposite direction of the gradient of that objective function with respect to this parameter which we are updating. And when we are going to compute the gradient, we will compute using chain rule, because this is not a single function. This is basically a hierarchy of multiple functions, and ultimately it is a very complex function. So for example, here you can see just one forward pass. Let's say this is word embeddings of some text, and this is word embedding of some text, and this is the value of w, and we have this as bias. Suppose somehow in any intermediate step we have this w at present and this v as present, then if you just do this one, then this is going to give us the classes course, and based on this we can say that that particular text for which this is the word embedding is basically belonging to the positive class. This we have already discussed, that what is the meaning of different neurons, more and more neurons. So more and more neurons means more and more non-linearity, because the activation function that generally we use, it gives the non-linearity. And this activation function and non-linearity is important, because if we do not have the non-linearity, then what is going to happen? Even suppose, let's say if this is our input, let's say this is the first layer, this is the second layer, third layer. Even if we have a lot of layers, but if there is no non-linearity, then all layers ultimately in effective is going to be basically collapsed in a single layer. It is not basically the multiple layers, because if there is no non-linearity, then all these basically layers we can represent using one layer. So that's why this non-linearity is important to have. And if we have more and more non-linearity, then it will have more and more capability to basically learn the distribution of the data, and that's what even we saw using one demo. There are different activation functions, and our job of the activation function is to introduce a non-linearity. So there are plenty of activation functions. Again, we will not discuss in detail, but the sigmoid is one of the activation function that was used in early days. But the sigmoid has a lot of problem, because sigmoid basically saturates for larger values, and for larger values, if it saturates, suppose if we have to compute the gradient here, then the gradient is going to become 0. And if gradient is become 0, then what will happen in our update? The W is updated only if I have some gradient value. If gradient value is 0, then there will not be any update, and that is basically called the gradient diminishing. If there is no gradient, then update will not happen, our network will not learn. So even there is another activation function TANH that was also earlier used, but the same problem exists with the TANH also. So let's have a look over this ReLU. So ReLU is basically called this rectified linear unit, which is basically one of the important activation functions that nowadays in practice, it works very well for the deep learning models. And even it is very less computationally complex, because it doesn't involve any exponential. If you see other activation functions like sigmoid or TANH, it involves basically the exponential functions. But ReLU is very simple. It is basically the linear in the positive regime, whereas it is 0 in the negative regime. So the only problem with the ReLU that it kills the gradients in the negative direction. For all, if the values are negative, if you're suppose if you have some values that you are getting, your activation values, if that is negative, then when you are going to compute basically the gradient, then for the negative inputs, gradient will become 0. Then ReLU is also going to suffer with the gradient diminishing problem, but only for the negative inputs. And but in practice, people have found that it works very well. There are some other activation functions. I'm just leaving now. If someone is interested, you can have a look. So Swiss is one of the recent activation functions that was proposed in 2018. And basically it tries to adopt the shape of the activation function somewhere in between ReLU and the linearity. So in case if the data is, if a lot of nonlinearity is not required, it may adopt the, because it has the learnable parameters will adopt in such a way that it will be more towards the linearity. But if more nonlinearity is required, then it will adopt in such a way that it becomes like ReLU. This overfitting, these things is even already covered even in the previous session, so I'm just leaving it now. Regularization is very important thing. So meaning of regularization is that at the training time, if our network is performing very well, then at the test time also it should perform very well. And if at test time it is not performing very well, it means that basically the model is overfitting the training data. And in order to avoid the overfitting of the training data, there are plenty of regularization techniques. And we are not going in very detail, but dropout is one of the technique where basically at the time of training, randomly these neurons are dropped, and there is some probability with which the neurons will be dropped. What will be the effect then? Suppose if some neuron is trying to learn some specific characteristic, then that will not happen, because there is no guarantee that that neuron will be available in any training iteration or not. So that's why the learning will be distributed among different neurons rather by learning only by few neurons, and that is basically going to lead to the regularization, where it will lead to the let's say better performance at the time of the testing also. Some other regularization methods are there, like batch normalization, where basically whatever batch of the data we have, that is normalized in terms of the let's say this geo mean and unit standard deviation, and then by that way also this regularization is increased. And tuning hyperparameters, there's this I am going to just skip because most of the time you have a lot of hyperparameters. What should be the values of hyperparameters? Then people can do different type of strategies to find out what should be the better values of the hyperparameters. And in fact, nowadays this Bayesian-based optimization is very, let's say, popular in order to perform the hyperparameter tuning. Loss functions, as I discussed, that for different problems there might be different loss functions or objective functions. For classification, we can have this cross entropy. For regression, we can have MSC, we can have MAE. Different loss functions can be there. So based on the data, actually there are different type of these deep neural networks. If you see, if your data is one-dimensional data, then we can have a simple deep neural network that we just saw. And suppose if you have a matrix of data, then we can have a convolutional neural network. And if we have a time series data, then we can have a recurrent neural network. And if you see, the convolutional neural network is basically, there is a convolutional filter. This convolution filter is also basically this W. So this is W, but this W is having, let's say, some values, and these values are going to be adjusted again using the same process of doing this backpropagation. But when it is going to compute the next value, when it is going to compute the output value, then this is just doing this convolution. Basically, this is not exactly convolution. Actually, here we are doing cross correlation, but the name is very fancy, this convolution. So people are following this convolution. So what happens, basically, we will just stride this filter across this image, across this input matrix in the horizontal direction and vertical direction, and just do the dot product and find out the value, and that is going to be basically the final value in the output. And the same suppose if we have the multiple such filters, then we can generate the multiple output layers here, and multiple output channels here. And even in a layer, we can have, let's say, X number of filter, then we can have X number of channels in the output layer. And similarly, we can have several layers like that. So for example, here, so suppose if this is the input and this is one convolution, similarly we can have even another convolution also here, then another convolution also here, another convolution also here, and that will again constitute to basically a deeper convolutional neural network. And if our input can be represented in a matrix form, then we can apply this convolutional neural network, we can apply this convolution operator, and rest of the processing is going to be same. That this is initially we are going to initialize these values of this filters, convolution filter, randomly, and then we will compute basically the class score, and ultimately the class score is going to be backpropagated. Basically, the objective function, the loss is going to be backpropagated, and these parameters are going to be updated so that next time it should perform better. So we can have, even with the multiple filters, we can have the multiple layers, and all those things are basically can be used in the neural network. How many number of filters, how many number of layers, those things are still fully not known, but people are trying to come up with the policies based on the scenario, based on the data set, based on other, let's say, aspects. Similarly, there is a recurrent neural network. So recurrent neural network is a neural network actually that tries to basically do some kind of a memorization, or tries to also see that what is happening at the previous time step. So for example, here, if you see suppose if we have a different words, let's say if you are going to process the different words, and let's say this is the current word, this is the previous word, this is the next word, and suppose that this is the current word, then it is also going to basically use that what we have already done for the previous word. So that information is also going to be utilized here. So that's why its name is called the recurrent, because if in an effect it can be represented like this, where basically when we are going to compute for xt, then we are also going to utilize the information that what was this ht for the previous let's say word, that is called ht minus 1. So in order to compute the ht, that is for the current input, what was the learned things for the previous thing, that is also going to be utilized. So there's a kind of a memorization, and basically that is leading to this recurrent neural network. There has been a huge progress in recurrent neural network also, like this RNNs, and there is a GRU, then there is LSTM. So there are different type of this recurrent neural networks which is available in the literature. And even we can have the mappings in a different way. For example, we can have one-to-one mapping. Means word in one input is coming, one output. Let's say one word is there, but we are generating multiple words as the output. Multiple words are as the input, but we are generating only one word as the output. So like that, even many to many is also there. So like that, we can basically have the different type of this recurrent neural networks. Even there is a bidirectional also. So bidirectional is going to basically make use even from the reverse direction. So if someone is interested, even you can have a deeper look over these architectures of this RNN, then bidirectional RNN. Similarly, we can have, let's say this is called sequence to sequence or encoder decoder based model, where we can use this type of RNNs to first basically do the encoding. Encoding means we will find out some representation, and that is called the latent space. And from the latent space, we can have the decoder, basically that can be again basically used to generate the output in the different forms. So suppose if you have to do the machine translation, means suppose if you have some words given in the English, you want to transform in some other language, then this can be also used, that encoder can transform these words into some latent space, and that latent space can be used again to transform in a different language. There is a GRU which is called gated recurrent units, are basically that is also based on this memorization, but it is going to have some gates. For example, there are gates like there is a this is a R gate, this is a Z gate. So this Z gate is basically here that is going to retain the information that let's say for the previous step, how much information we should use, whereas this R is the reset, basically that suppose if something is for the short term, let's say if you have some words which has short term dependency, then this R is going to be very active for that. But if there is some word which has the long term dependency, then this Z is going to be very active. So like that, basically this is going to retain the information not just from the previous word, rather previous few words information it can retain. Like this. In fact, there is another model which is called this LSTM, that is called this long short-term memory. But GRU is very commonly used. LSTM is also used. If someone is interested, you can have a deeper look over this these recurrent neural network models also. There are plenty of applications in natural language processing, like this machine translation, this sentiment analysis. Suppose this is one example of IMDb movie reviews. That is also sentiment classification. There can be a lot of examples where relation can be extracted from the text, and a lot of things can be done by using such type of these neural networks. So due to interest of time, we are not going to even much deeper in these things. Now we will restrict it here, and we will just finish this task, this topic here. These are some these are some of my research area. I'm not going to discuss it due to the time constraint. Yeah, but anyhow, if you have any questions, then I would like to take some questions.
Thank you, Dr. You're on the way. Now, if there are any questions, please raise the questions. One or two questions will be. You can ask any question actually.
I think this is lunchtime, so people might be waiting for the lunch.
Medical field, some question is there in the chat box. For what application RNN will be better than CNN? There is one
For
question.
what applications RNN will be better than CNN? So basically, if you have to utilize the time information, so if you have a time series related data, then RNN will be useful. Means if something is going to be dependent upon, let's say something which has done in the past. For example, suppose if you have a sentence, and suppose if you are processing a last word of the sentence, and then it is the meaning of the whole sentence is not going to be dependent only on the last word. It is going to be dependent upon all these words which is coming from the starting. So if you are processing some words, even which is later, we have to also utilize the information that was basically conveyed by the previous one. So wherever we have to rely on the characteristics or let's say the properties of something which has appeared in the past in terms of the timing of this computation, then basically we can have the RNN. And suppose if the same thing is happening even in the image data also, or two-dimensional data. For example, if we have the video, in video we have the frames, then frames are also having the time information. So suppose if someone is punching, then basically we have the information, we have these frames like this, then this time is also there. So there even RNN and CNN both can be used together in order to deal with such type of problems. If there is no time information, let's say if you have to do simple image classification with just one image as the input, then RNN is not required. Then only CNN is fine because there is no time information there.
So sir, I have a question.
Yeah, I would like to add to okay, Sivaram. It is basically a sequence. If it is a sequence,
yes,
process a sequence, then RNN may be better.
Yes.
Yeah. The next question, please. Yeah.
Sir, I have a question. So, what activation function is best suitable for RNN and NLP related data?
So very soon my survey paper will come on this. It is under review. So I have done experiments on that, and I have evaluated 17 activation functions. So basically there is no hard and fast rule. But if you see the basic activation function, which is ReLU, generally it is better. But what I have noticed that even activation functions like TANH, these are traditional, but they are even giving some good performance even in case of the problems like machine translation. So still there is no hard and fast rule, but there are some activation functions which are coming nowadays, which is data dependent, and those activation functions are doing very well.
Yeah, thank you, sir. So in medical field, can we rely on a sigmoid, or do we need to focus on some other activation function?
So if you are dealing with the image data, then sigmoid is not good at all. Then you have to start with the ReLU. You should use ReLU or some better than ReLU, and there are a lot of improvements in ReLU, but those improvements are not consistent. Means it is giving some good performance on some data set, but not on other data set. So that's why ReLU is still one of the popular choice.
Yeah, thank you, sir. So in hidden layer, some of them are using some activation function. In output layer, some activation functions are used. So what is the trade-off between these two? So in hidden layer, what activation function is required? In output layer, what activation function is required?
In output layer, basically, we do not have any activation function. In output layer, we have the, suppose if you are using some classifier or something, then we have to use that to generate the class score. So for example, suppose if you just use a sigmoid, then that class score will become probability because it is going to give us the values in between 0 and 1. It is very much related to the probability.
Yeah, thank you,
so
sir.
For example, suppose let's say if you are doing some regression task and it has to generate some real number, then we cannot use any such an activation function because we cannot restrict in between 0 and 1 or something like that.
Yeah, thank you, sir.
Any other question?
Someone has written, easy to understand maths part. I am from maths department and take time to understand CNN and RNN. The mathematics for deep learning is very easy because it is still the black box. So only some optimization things are there, which is generally you can have a look in from the mathematics related stuffs. But most of the time, even this gradient computation and all those things, in reality, if you are going to implement, generally you do not have to compute it because the frameworks generally that you are using, let's say TensorFlow, PyTorch, or Keras, you can find this ready-made implementation.
But I would like to add one thing. But the mathematics knowledge will be useful in doing research. Maybe you can invent new activation, new loss function.
Exactly. Yes.
So mathematics knowledge may be very much useful.
Yeah, mathematics knowledge is useful for the analysis part, and there basically you can look from the gradient perspective because this whole optimization in this deep learning is happening based on this gradient descent, and then what kind of how it can be improved in terms of different layers, or even in terms of the strategy, even for doing this optimization.
Any other questions, please? So, if there are no more questions, then let me thank Dr. Sivaram Dubey for this wonderful lecture. So, we will meet at 2:30. There will be a good lecture on stress, peace, and philosophy. So, let us please join at 2:30. So, thank you.
Okay, sir. Thank you very much, and thank you very much, everyone, for listening the talk. So we can now just get disconnected. Thank you, everyone.
Thank you, sir.